Alright, silly people, here's the situation. Look at this giant wall of text of a physics problem that we've got to do right here. Um, so this is a diffraction grating problem. This is a classic like quantum physics sort of thing where we're going to be shining light through a diffraction grating and then showing it off once it goes through a lens on a screen where the intensity of the light given a position on the screen is given by this equation here. Um, and this is a thing that we have to do, and we have to display it. So um, first of all, consider a grating with a transmission function q of u. What is the separation of the slits in terms of alpha? Turns out if you're given the separation of the slits in terms of alpha, because the sine function actually determines the magnitude of the uh, intensity of the transmission, right? And then that sine tends to have peaks around pi values separated. So every pi value that you're going to have a peak. So that means that your d, your separation should be about pi divided by alpha, right? And then we actually put that in LaTeX for nice reasons. So pi alpha. Yeah, that's really all it's trying to get at. So that whenever you plug in your value of separation that it gives you, you can calculate alpha from that. That's not too complicated. And then the next thing is write a Python function that q of u that returns the transmission function sine squared of alpha times u. So that's incredibly easy. So we can do, I'm going to go ahead and import some stuff. Import numpy as np because I know we're going to need some square root stuff. I'm going to also import matplotlib.py plot as plt because I know we're going to plot stuff, and also import cmath as seam because there's going to be a bit where we use the cmath version of the exponent function to calculate this guy because that's an I in there, right? But yeah, so we just define q of u. It's going to return the numpy sine of alpha times u all squared. And I'm going to define alpha outside because d, according to the problem statement, is 20 microns. So d is 20 e to the minus 6. We can have alpha be just pi divided by that. So then that should return a good function, right? So part C, use your function to calculate and graph the intensity of the diffraction pattern produced by such a grating with having 10 slits in total. This is interesting. So we need to do this via Gaussian quadrature, right, or any other integration method. I'm just going to do Gaussian quadrature. And as always, we're going to define the integrand separately and then call upon the integrand when we start doing the integration method. So I'm going to do def f of u and x. Needs to have both in there, which is going to be returning the square root of q of u times cmath exponent, going to say 2j in parentheses, j being the computer equivalent of I, and then that is multiplied by pi times x times u, and is divided by lambda times f, right there, lambda times f, and those are things we have to define. I'm not going to call it lowercase f though, I'm going to call it lowercase fl for focal length, just to differentiate it from the function. And so lambda, again, according to the problem statement, is 500 nanometers. The focal length is 1 meter. And so now that function should run. And then we'll create a function to calculate the integral itself. I'm just going to call it I of x as per this notation. And it is just the integral of that from minus w over 2 to w over 2. And then you take the absolute value of the integral and you square it. So what w actually is in the context of the integral, though, is not the same as the total width of the screen. It's actually kind of given to you in a subtle way. All it's saying is that you're doing a grading with 10 slits in total. So you need to just have whatever separation you have times 10 to get the 10 slits. So we're going to do W equals 10 times D. Right, that should be cool. Now you can just sort of do the Gaussian quadrature bit. You're integrating from minus W over 2 to W over 2. I'm going to say a nice big sample size of n equals 1024, and then create a couple of variables from the Gaussian quadrature. I'm just going to use the shell of Gaussian quadrature that I've been using for the past several videos. So that's going to be, you create an x and a w. That is the result of Gauss xw of n. You create an xp list, which is 0.5 times your b minus a times your x plus 0.5 times your b plus your a, and then your w list is going to be 0.5 times, again, b minus a times your w. And I'm just calling it xr and were instead of x and w because x is something which is defined as an argument of the function. So once you have that, you set up your sum, s equals 0, you do 4k in range n, and you add on to your s, as per the usual, just wp indexed k times f of xp indexed k. But since u is the integration variable in this integral, right? But then we made our integrand also a function of x in addition to u. We do need to put comma x in that function call. After that, though, you can return the absolute value of s squared, and it should have completed the integral in a clever way. And then, yeah, we just have to display now the diffraction on the screen. So for x, and let me actually create a input list, xls, which is going to be length space, which is going to run from minus 5 centimeters to positive 5 centimeters, because it's a 10 centimeter wide screen with 1,000 points for high fidelity, and then you do for x in xls, create a output list, which I'm just going to call ILS, and you append the output list with I of x. Pretty cool. And then at the end you can plot XLS versus ILS. And that should run. But it is going to take a while because, as it turns out, doing 1,000 sample points for the input list, but then each of those 1,000 points you have to do an integral, which is taking 1,000 samples from the thing. So it ends up being 10 to the 6 calculations, so a million calculations pretty much, that it's doing to get this integral out. So yeah, it's going to take a second. And this isn't even the best way to display it, really. Not even the fastest way to run the code. And of course, there's other integration methods which run faster, but this is sort of the way that Newman wanted us to do it. So a few seconds, I think it should be close to done. Let's go. Aha. So yeah, that's the diffraction pattern shown on the screen, where the x-axis is the position on the screen and the y-axis is the intensity. Of course, the next part of the problem is to not just display it as a line plot, but also display it using a density plot. And that's not actually too difficult to do. What I'm going to do is I'm going to use the fact that we've already calculated the thing, and I'm not going to calculate it again. Instead, I'm going to take what we've got and create an I map of it using a NumPy function called tile. What it does is it takes as input a list of data, and then you just make it so that the data, instead of being the format of a one-dimensional list, it's a 100 row list where every row is the same list, so 100 by 1. And then you can very easily use the imshow function from Matplotlib and just imshow that. And it shows a really nice diffraction pattern, and I even think that the color map of jet is better for our purposes. You can very clearly see the sort of pattern, and you can even increase the amount of rows that you have. I might even do 300. That might be too many. Maybe 200. Yeah, that'll show up nice on the video. Very clear diffraction pattern if you use those settings. Okay, so that's just the first part of the problem, of course. The next part is to, modify it to use different transmission functions, right? So the next transmission function it wants us to try is q of u equals sine squared alpha u times sine squared beta u, where beta is alpha over 2. So that shouldn't be too hard to implement. We'll just do beta equals alpha over 2, and then multiply this guy. Let me put this sine squared in parentheses so it doesn't get mixed up. But we'll do sine of beta times u, not beta of u, but beta times u. Yes, and then square it. That's the only thing you have to change, really, and then you can run it through again. And there we go, a minute later, it's finished running. There's the line plot of the diffraction pattern. It doesn't look too different from what we had previously, actually. Just a little bit more like prominence towards the middle of this separation here. But yeah, not too different from what we had before. The next and final transmission function we want to try is 2 square slits with 100 transmission through the slit and 0 transmission everywhere else, with two non-identical slits. So again, the only thing we have to change is the transmission function. And so it's not going to just return a function. Instead, it's going to return, if it's in one range, it's going to return 1. So let me just write that right now. If it's in some other range, it's also going to return 1. Otherwise, it will return 0. And let's think about how we define those ranges. So one of the slits has to be 10 microns wide, and the other 20 microns wide with a 60 micron gap between the two. So if we have it be the upper limit on this range, minus 30 microns, and then the lower limit on this range being positive 30 microns, that takes care of the 60 micron gap between the two. As for the lower bound on the top one, we'll have this one be the 10 micron wide one. So we'll just have it be between minus 40 microns and minus 30 microns. That's 10 microns of transmission. And then this is going to be 20 microns of transmission, so we'll take this up to 50. Right? Those should be the correct ranges, and then otherwise it will return 0, of course. Should also definitely change W, the total width of the diffraction grating, because at this point you've now changed it from a sine function grating to just a binary grating, so W now has to span this entire range. So 50 microns minus 40 microns makes about 90 microns. That might change some things up when we get back to the diffraction pattern, but I'll see you in a minute. Okay, there's the line plot. It looks pretty wacky now. Of course, it's going to be easier to see the difference if we switch over to the diffraction, like the density plot. And I don't know if this is going to show up on the video or not, but this diffraction line is a little bit more of a darker red than this one, and this is a brighter yellow than this. It's a little bit wider as well on this side than it is on this side, and that just sort of is trying to reflect the fact that we have different gratings on either side of the 0 mark, but it's a pretty different diffraction pattern, all things considered, and not exactly what you would expect straight away from this sort of function. But yeah, that's it.